Good afternoon, ladies and gentlemen. Hope we're doing well today. It's great to get started, but I'd like to give everybody a couple of minutes before we kick the tires and light the fires. So stay tuned. I'm going to change the banner here. And yeah, so let's get started here in 2 minutes. So grab your coffee or your water and meet me back here. Sweet. Sweet. To save. Boom. Look at that. We got everything working for us, folks. We got one more minute and then we'll start the show. And this is a great presentation. This is one of my favorites. I get into a lot of detailed discussion. And hey, do me a favor. When you show up, say hi. Don't be a stranger danger. You have no audio. Uh-oh. Somebody else, please let me know if we've got an audio issue here. Yeah, it says my mic is open. Hold on. Can everybody hear me, or audio and video are good? Thank you. What's going on, everybody? What? We got Muhammad Magoo. We got Mallory. We got Steve. We got Gene Schaefer. Steve. Mallory's texting. All right. It looks like, let me go up to Andrew. Andrew, check your speakers, brother. All right. Awesome here. Volume is all the way up. Andrew, if you go to the right-hand side of the screen, there are 3 dots in the upper right-hand, blah, blah, blah. That's where you should be able to, or underneath there is a gear that says settings. And Scott DiLoretto, your video's a little rough. You know, always leave it to Scott. He's so mean. Scott, I'm going to shut down the video here so we can check out the slides. And Matt, thank you for joining us, sir. Matt Howard, ladies and gentlemen, amazing writer. Yatin Sri Harsha. Man, we've got a bunch of people. Okay, everybody, let's get started here, huh? Andrew, what I'll do is, if you can't get your volume working, I'm going to download this, turn it into a YouTube, and then send you the link for that, Andrew. I'm going to send you a recording afterwards, buddy. All right, so let's go ahead. I'm going to remove my video, add to stage. And there it begins, everybody. Let me get rid of this. Short course number 6. Do not forget to reach out to Mallory and Whitney to ask for a certificate for going through this course. And look, Andrew already sent his email. Can you grab Andrew's email?
Yeah,
or send
I'm
him?
just getting on right now.
All right, Andrew, we got that for you, man. Yeah, no problem, bud. Okay, so, and Andrew, if you want to shoot Whitney a message with your phone number, we can call you from my phone so you can hear it from my side. All right, let's get into this presentation. So, good afternoon, ladies and gentlemen. My name is John Belkwitz, and I am here to present to you today what we like to call the magical world of concrete. Let me know if it starts buffering, but I like to show my face when I do this. You know, I have some expressions. You know, I've got great eyebrow control. This short course is all part of a series where we dive deep into the impact of nanosilica size and surface area on the concrete composite, as well as the hydrated cementitious matrix. Everything okay? Fantastic. Pleased to meet you. My name is John Belkwitz. I've been in the concrete industry for a very long time, since I had a full mane of majestic hair. Started my occupation as a mucker's apprentice when I was a young kid. Get the equipment out before school, and if I was lucky enough at the end of the day, I would not only get to clean equipment, but I would learn how to finish concrete. Made my way into the United States Air Force, where as part of a civil engineering squadron, our job was to provide, prepare, and sustain bases, the platform for the projection of aerospace equipment around the operational continuum. What that meant is I got to meet new people, place concrete with them for the greater good of the United States Air Force. Years later, I got to go to the Air Force Academy, the Colorado School of Mines, and then so on and so forth with other degrees, all of which with focusing on how to better my understanding of concrete hydration, cement hydration, and the optimization of the concrete composite. Years ago, Whitney and I, gosh almighty, 15 years, 16 years ago, we started Intelligent Concrete with the idea of bringing new and emerging technologies from what is sometimes a university basement or somebody's garage, right. And bringing it out to the industry or solving problems in the industry. And we've been doing that, Steve, will do, sir. We've been doing that for 15 years and having a good time doing that. And that includes colloidal silica and concrete. And it's got to be one of my favorite technologies out there. This is a book that I wrote on the subject. And funny enough, the book is titled An Analysis of the Use of Nanosilica to Mitigate Alkali Silica Reaction in Concrete. And it was an awesome project. And I'm going to be going some of the research that we dove into for that project. And gosh, I wish I could go through the entire thing, but of course, with time constraints, and I want to give you all time to ask questions that are going to challenge not only the subject, but challenge me too. You might help me figure out another avenue for research. And if you stump me, you get a steak dinner. No, you get a t-shirt. T-shirt, not a steak dinner. That's crazy. So before we get into the meat of the presentation, I'd like to give you a quick overview of what we're going to be talking about. The roadmap, I'm gonna copy and paste it so you'll get to see. And I'm gonna kill these comments for a second. I'm just getting a little bit distracted. I'll revisit the comments when we get to a pausing point. So every time you see this overview slide, that's a pausing point while I'll go back to comments. So here's a roadmap of what we're going to be doing. First and foremost, for the folks who don't know what ASR is, or they know what ASR damage is, but they've never seen it in an explained breakdown or an illustration, we're going to do that. After that, we're going to go into the basics of nanosilica. What is nanosilica and the different types out there? And then from there, it's analyzing data. And we're not only analyzing the accelerated mortar bar test, that's the first thing, but we're also going into an optical microscopy and scanning electron microscopy analysis, which is pretty amazing. After that, we'll wrap it up with a concise summary and then open up the floor for any questions. All right, so let me see. Oh, sweet Caroline, we've got some questions, emails. Whitney and Mallory are collecting these emails. Sri Harsha, we have a book called The ABCs of ASR, and this can be downloaded for free. Army Corps was gracious enough to pay for that. Okay, Muhammad Goob sent his email for us. We will send that to you, sir. Okay. For my nano silica enthusiasts, or for my ASR enthusiasts, please forgive me as I take some artistic liberty with explaining this in a very short, concise set of time here in slides. So, our concrete national infrastructure is made up of over 600,000 bridges, concrete bridges. This establishes a $48 billion a year industry. Now, of that, $8.3 billion is put back into the maintenance associated with physical and chemical attack. Now, I'm not saying that concrete is broken, but we do need to figure out a way to enhance the durability. And if you're of the mindset that, well, John, that's fine, but we're talking about concrete that's 20, 30 years old. Like, who cares? We've changed mix designs. You're not wrong. And we need to address the problems from concrete 20 years ago was concrete 2005, which is not that long ago, especially concrete bridges at that point were designed for 100 years. So as it turns out, there are many bridges throughout the Western US, Midwest US, that are at their 25 age or 25 years old out of 100 years. And they look like this, water reclamation project here that has some beautiful Isle of Man cracks and just some gel oozing out of it. And this isn't a surprise to us. We should have seen this coming as concrete producers, as contractors, as engineers. We don't even have to be that involved in the industry I work for a living and I'm not in the academic arena, so I don't go to these associations, isn't an excuse anymore with the World Wide Web. Just Intelligent Concrete and their employees alone, we have somewhere around 100,000 folks who get to see what we share every day for the last few years. And part of that is the herpes of concrete or alkali silica reaction. And again, we've seen the changes. The use of higher alkali cements in the late 90s through the early 2000s, all the way to the 2010s. Then through the 2010s and maybe through the early 2000s, the use of lower alkali or lower quality reactive aggregates. And the unfortunate reality, it's been buttoned up with ineffective pozzolans. Now, some would say that since we're dealing with problems, there are cements and low carbon concrete methods that are introducing a cacophony of errors that we have yet to deal with. I wouldn't argue that. But let's get into ASR. ASR, somebody who deals with this on a very high level, ASTM wise, one said that ASR is not and will never be the primary failure mechanism for a concrete structure. Remember, he made me take it out of my paper. It was funny enough, 3 months later, he used the same kind of statement that ASR, the first time ever, ASR is that primary failure mechanism. So if you've never seen ASR, what we've got here is a reactive aggregate, and normally that aggregate has a tetrahedral form of silica that is susceptible to a breakdown because of change in pH at the interfacial zone between the hydrated cement paste and that reactive aggregate. Now, within that hydrated cement paste, there is a wide variety of salts within water, and we call that a pore water solution. Now, it happens to be that the alkalis within that pore water solution, sodium, potassium, as well as calcium, breaks down the reactive silica and redistributes, reorganizes it from monomers to dimers and oligomers in a polymer into this hydrogel that has an expansive nature at that interfacial zone between the hydrated cement matrix and our aggregate interface. As more water is imbibed into that hydrogel, and that hydrogel expands from a hydrogel to almost like a superabsorbent polymer, there's a residual stress induced in that confined zone. And at a certain point, that residual stress overcomes the sheer and tensile capacity of our hydrated cement matrix, and in some cases our aggregate, cracking the concrete, inducing more water and salt flow, It's just a vicious, nasty cycle. Now, that being said, when you look at it under a scanning electron microscope, it's beautiful. I mean, this is what they call, or what we call, an ASR gel rosette. And I made sure to include the scale here. And the beauty of it is compounded by, you know, uh-oh, I'm gonna kill my camera. We're having video problems here. Hold on, let me see. Okay, so this is a higher magnification of that ASR gel rosette, and you can see I'm trying to focus on those little nodules there at the center. And as I get closer, and hopefully the image isn't lagging, you can almost see like some of the individual fibril morphologies, these wispy like needles that are interlocking. And oh, we're going to get a little bit closer, but this is the mechanism behind the ASR gel bringing or drawing in more water, and then having that ability not only to survive in that hydrogel-like state, but also thrive to go from a mature to a new gel or an immature state, which again is often contained within a shell that is then confined, that then creates more stress. And I think that's the highest zoom that I have on this. And it's just so gosh darn pretty to look at those. And if you've never read her paper, Kim Curtis, back in 1996, and I brag about this paper way too much, did a paper on soft X-ray gel spectroscopy, microscopy. I can't remember what the last word that she used, but basically what she was looking at is this fibro-like morphology of the ASR gel rosette. And why that's important is because we have these needle-like fibers or fibrils that are crossing over each other, creating these pores that have extremely large and then small diameters all the way through it. What that does is it creates a capillary suction that draws in not only the pore water solution, but the salts, which will induce more expansion. Now, again, I want to remind everybody, this wasn't a surprise to us that this ASR issue was not only going to be an ongoing problem, but it was going to get worse. Those three things that I brought up earlier, those weren't my words. And I'm not trying to plagiarize. Here's a great recommendation for you to read. This is by Katie Barget, Kurt Von Fay, and a couple other folks at the Bureau of Reclamation in Denver, at the Denver Federal Center. And they came up with a great paper on new recommendations for ASR mitigation. And they cite the three reasons why ASR was going to get so much worse. And it literally is in the front of the document. You don't have to go the 60 pages to the conclusion to find out what's going on. So we knew about this. Now, the objectives of this, now that I've created the doom and gloom, the objectives of this next part is I want to introduce what Nano Silica is. I want to go into why should we care about using Nano Silica as a tool in our ASR mitigation box. And then from there, we're going to review the data, not only the AMBT, but also on this ASR gel pat test that we did. And then we're going to wrap it up with a concise summary, analyzing the key points and the direction for the future. And then, of course, we're going to open up for any questions. Okay, let me see. Do we have any comments, questions? Did you see any, Whit?
No, I don't think so.
All right, come on, y'all. Start coming up with good questions. I got a bunch of T-shirts over here. I don't have a bunch of T-shirts. We have a few T-shirts. Okay, so what is Nano Silica? I think I might have uploaded the wrong presentation. We're going to find out here in a second. Let me see. Yeah, we'll see here in a second if I have to change over. Man, oh, shut it. Yeah, hopefully this is not the wrong one. Okay, so nanosilica is a liquid dispersion of nanosilica-sized particles, not affected by gravity, clear to milky appearance. The specific surface area is anywhere between 30 to 2,700 meters squared per gram. Solid content can be anywhere between 15 and 50%, and your pH has a maximum of 10.7. Now, thank you, Brian Green and his crew from their paper on ultrafine amorphous colloidal silica for a rock matching grout. And this is a colloidal silica or nanosilica dispersion. And just a quick hack, concrete hack for you. The larger the particle, the more opaque or milk-like the colloidal silica dispersion. The smaller the particle, the more it looks like water or water with a blue and greenish tint to it. Now, when we put this technology under a microscope, I like to set up these references to give you all an idea of what we're dealing with here. And just to give you a reference, like a human hair, obviously not on my head, is around 100,000 nanometers in diameter. For my concrete folk over there, left-hand side, our fly ash that we traditionally use, that poor man's water reducer, pozzolanic reaction, when we put it under an electron microscope, we'll see it somewhere between 1 micrometer and 100 micrometers. Here we see it around 10 to 20 micrometers in diameter. Using a similar, not the same, a similar electron microscope, when we look at nanosilica, it's around 10 to 20 nanometers, effectively 1,000 times smaller than our fly ash. And because it's smaller, we're going to have some different positive benefits that we can take advantage of, not only for other value-added performance like abrasion resistance, permeability, but also alkali silica reactivity. Now, what's so special about nanosilica? First of all, nanosilica, we have this free silica surface area for pozzolanic reaction. I often refer to the team. Land and Steven wrote a paper back in 2012 that talks about this instantaneous pozzolanic reaction that they refer to as calcium silicate hydrate seeding effect. Now, because you have that accelerated calcium consumption of calcium hydroxide to develop more of that strength-bearing structure of concrete, that calcium silicate hydrate, you have a greater, or you have a higher degree of cement dissolution. We call that accelerated cement dissolution. Two great papers, Bjornstrom et al. Back in 2003 and 2004. And then finally, because we're dealing with and what that basically means is we're getting a higher dissolution rate. We're getting more bang out of one cement particle compared to what we would do without that nanosilica technology. And the last piece of that, what makes nanosilica different from other particles that are in the micron realm, is something called heterogeneous nucleation, which is a very fancy way of saying, because we have a very small particle, it has a very small force field on it, and therefore other things will want to grow on that particle because of said smaller force field or electrical double layer. And I illustrate that here with my micromillimeter sized particle versus the nanometer sized particle on the right. Those change in force field. Okay, so let me just check the, what's it called? Let me see. I really hope I didn't screw that up. Oh no, I think I did, Whitney. Everybody, I might have to change slides here in a second. Maybe not. We'll see. If not, it'll be a quick change. Okay, comments. What comments do we have? Does nanosilica increase abrasion resistance in concrete? Yes, Sri Harsha. Ooh, let me show the questions. Yes, we've been seeing that for a long time now. But again, if you do a quick Google Scholar search, Or if you're part of the ASTM, I think it's 0924, our committee to make an ASTM for colloidal silica in concrete, then you'll see some of the different references that go back to abrasion resistance. Are there any health issues for inhaling silica dust? Yes, but Yosef, we're not talking about silica dust here, man. That's a topic for a different conversation. Yeah, and Silica Fume Association does a very good job of talking about silica dust, but yeah, this is not dust. This is colloidal silica or nanosilica sized particles in a liquid dispersion. And when said things dry, they agglomerate into these big old chunks that don't plume into the air. And that's Yosef's question. And then, hey there, what about the particle size in nanosilica? We're going to get to that here in a little bit, Hader. Ranit, I did trials with nanosilica 0.3% with 2 different cementitious. Awesome. But did not get significant strength gain. I've also observed shrinkage cracks after hardening. It sounds like, Ranit, you need to use a different type of nanosilica. Would I think if you saw any type of strength gain, especially if it was early strength gain, you might have been using too small of a nanoparticle size, like a 3 to 5 nanometer, especially if you have observed shrinkage cracks after hardening. We can get into what better types of nanosilica there are out there for it, but basically you want to go for a larger particle size, ultimately to control that hydration. But I would need a lot more information, Ranit. Shaman abrasion test. Josh, you lost me, buddy. We do the ASTM-C 779 procedure C. Then we also do ASTM-C. That one's the steel balls with water flow. Then there's the underwater one, the 1130, and then there's the D4060. And then there's the 944, which is the Chaplin abrasier shtick. Yeah. Oh, whoops. All right, let's get back to this. All right, so mortar bar design. Oh gosh, is that number right? Yeah, see, I think this is the wrong presentation. Oh man. So if I screwed that number up on the 20%, I apologize. Yeah, it looks like I screwed that up. Sorry. But it's it's supposed to be the opposite. It's supposed to be 990 on aggregate and 440 on cement, and I switched those two. I apologize profusely. That was not intentional, but you get the idea. Here's our colloidal silica packages that we used. We used 3 different types. They were narrow distributions, 3 to 5 nanometer, 9 to 11, and 45 to 47, to give us those 3 different specific surface areas. And then from there, man, is it cutting off the bottom?
I don't think so.
Can you see dose 4?
I cannot see. Mine is showing the overview slide right now. I don't know why. Let me refresh.
Hold on, folks. Okay, I'll keep going, assuming that we're doing all right here.
Yeah, I can't see those.
So what we did is, you know what? Why don't you shut yours down? Maybe you're drawing on some of the internet for this. So what we've got here is 3 discrete or narrow distributions, and what we did is I used them at 4 different dosages, where the first dosage represented an equivalent amount of silica that would be brought by 20% class F fly ash. And then from there, we increased it by 1 order of magnitude, so to 200% fly ash, and then 2,000, and then 4,000% equivalent. Now, we couldn't do a replica of that using class F fly ash in any of our mixes, so we stuck with that 20%, but we ultimately used colloidal silica that would have the same amount of that specific surface area of reactive silica as the class F fly ash, and then, of course, those increased dosages. And what we did from there is ran the ASTM-C 1260, which is your OPC mix. And then the 1567, which is your 20% class F fly ash mix. And then what we did was we ran mixes that had a replacement of cement with colloidal silica that matched up to that chart. And what I'm showing you right now, that CS1 was the smallest particle, and you could see it at all 4 dosages. Now, we took this out to 28 days, and of course, as you can see, starting from 3 days, there was some immediate expansion, but as we get past our 14 and go to our 28 days, that smallest particle, that 3 to 5 nanometer dosage, whenever we used it, there was a lower rate of expansion at our final 28 day, and pound for pound was much more efficient even when we went to our highest dosage. The same can't really be said for the 9 to 10 nanometer size particle. And we'll see this as we go even to the 45 nanometer size particle, where that larger particle, because it doesn't have as much reactive surface area as the smaller particle, you need a lot more of it to kick off that pozzolanic reaction, stable that environment, and do something with the pore water so that it won't interact to create more of that ASR gel. Not only do we see that with the 9 to 10 nanometer particle, but we also see that with the 45 to 47. Not that it's not giving us good results, but if we want similar results that we had with the small s particle, we need a significantly higher dosage. And that's where a lot of people come up with the same indication that I think it is Sri Harsha who said that, hey, and I'm not looking at the comments, I apologize, we used this at 0.3% and I didn't see good results. Okay, you might have been using too much. You might not have been using enough. You might have been using a cement that doesn't work well with nano silica or colloidal silica, and it could agglomerate it as soon as you distributed it into the mix. You might not have mixed it fast enough. There might have been a mid-range water reducer in your mix, so on and so on and so forth. So just because it didn't work once doesn't mean it'll never work. Just means you need a better combination of colloidal silica to your binding and admixture matrix. Okay, so let's get back to how does the ASR work, and how does the nanosilica size and surface area impact it? And like I said, we have these much smaller particles. Every single dispersion that we're using is very discrete. So we know that there are certain mechanisms that are happening with the smallest ones that are not happening with the largest ones, and vice versa. And as it turns out, with the smallest particles, and you can go back to a lot of the research, not only the research that we've done, but a lot of folks from other universities from all over the world that show that those particles that are really, really small have a tendency of burning up faster and getting lost in the hydrated product. And we have to question whether or not it's nanosilica anymore, or is it now chemically incorporated into the calcium silicate hydrate network. Now, what's great about that stuff is it has an immediate interaction with the pore water solution, doing something that would otherwise cause ASR expansion. And there's some wonderful papers that I've been reading on the role of portlandite or calcium hydroxide, the need for that for the ASR expansion, ASR gel expansion to really kick off. Now, with our larger particles, they might not kick off that pozzolanic reaction as quickly, but what we found with those larger particles, 9 to 10, 45 to 47, even up to the 100 nanometer, is that we're creating a hydrogel that, even though it's not chemically incorporating it to a calcium silicate hydrate network, it's binding those alkalis that would then normally contribute to the ASR gel mechanisms that we talked about earlier and referred to in this image. Okay. I love this test. So this is a British standard. I don't like the American version of it. It's BS 1493. Anyway, 14893. The ASR gel pat test, and it is such a friendly and lovely test. You're taking your aggregate, grinding, grading, and washing it to a 1 to 2 millimeter gradation. And then you are putting it in a very thin paste almost like a pervious mix, curing it for a 72-hour period, grinding the top paste off, and then from there, putting it into a pour water solution for 72 hours at, I believe it was 125 degrees Fahrenheit, somewhere around there. And what you do is first, it's an accelerated polymerization test. So you're looking at the ASR gel in an undisturbed state. And the two things that you're looking for is not only the presence of the ASR gel, but you're also looking at the morphology and the chemistry of those ASR gels under, really awesome microscopes. We'll get into that in a second. But here we're using an optical microscope. And the white stuff that you see on the left is that ASR gel. And we're publishing a wonderful paper on this through Company 33. The paper or the image on the right is that same type of sample, but now we've put in dose 3 of our larger colloidal silica, or our CS3, that 45 to 47 nanometer. And you don't need to be an expert to see that there is a major difference between the amount of gel that we can find on the surface of Portland cement or cement by itself versus the amount of nano silica that we used on the right. There's almost none present. Now, when we look a little bit deeper into the ASR gel, looking at that ASR gel morphology, the rosettes, if you will, not only do we see a change in the presence or the amount of ASR gel, there's a change in the structure, where those wispy-like fibers, they become thicker elements, changing up the diameter of those pores, reducing the tendency for the ASR gel to absorb solution. Not only did we look at the topography or the structure of the gel, but we also used elemental or mass species analysis in our scanning electron microscope to look at what the gels were made up of and if there was a change. Let me just get to it. What we found from our gels is that there was an increase in silica content, a reduction in calcium content, ultimately creating an environment that was not conducive for ASR gel polymerization. And, we also showed that there was a major change in sodium and potassium in these gels. But the reason why I referred to the the calcium hydroxide or the Portlandite is from this paper that, oh my gosh, it's such an awesome paper by Xiao Qiang Ho, Leslie Struble, and James Kirkpatrick on the formation of ASR gel and the roles of calcium silicate hydrate in Portlandite. And there's this thing in here that refers to, one of Michael Thomas's papers, who was a huge freaking fan of, and just stating how, in the absence of calcium hydroxide, they didn't see ASR gel polymerization kick off. So with using that nano silica, not only are we consuming more of that calcium hydroxide, that Portlandite, to create more calcium hydroxide, but we also see a reduction of that in our gels. And of course, that increase in silica is breaking the pessimum, or the oversaturating our ASR gel with silica, so we don't see that not only surviving, but that thriving of that ASR. Okay, so let me check out. Holy moly guacamole, we got questions. Yes, the Chapman abrasion, Josh. That is correct. Chapman abrasion. Did I say Chaplin?
Yeah, Chapman.
Okay, Chapman. I like the shaman abrasion test too. I just never seen that before. It sounds cool. Sri Hasha. Okay, yeah. I mean, Sri Hasha, it could be that you have the wrong type of colloidal silica. Shoot me a message. Maybe we can discuss it. Especially, don't forget, as you're part of the Colloidal Silica and Concrete Association, that's a part of your membership. Is help me out, Whitney.
Advocacy.
There it is. Advocacy and support for using colloidal silica and concrete. for all members, no matter what type of membership you've got. So please, your member, reach out and we'll be more than happy to help you out. Okay, hopefully I can get back to this slide. Okay, and then no. Sorry, I don't know what no means. Cutting off the bottom. I know, Steve. I know. I'm sorry. We'll figure that out. Does the nanotechnology add any positive attributes with the type 1L cement's difficulty during placement? What are you talking about, LinkedIn user? There are no problems with type 1L cement. Absolutely. We've been seeing some great value-added performance when it comes to using type 1L cement. And normally that's short-term benefits. There are some long-term, but as it turns out, the type 1L cements are really causing, that's a topic for another discussion. Quick question. Do you observe significant change in the reality? Yeah, absolutely. Oh yeah, Mahdi, absolutely. We do an entire YouTube video on using Nano Silica to bring back a mix from segregation, using different Nano Silica sizes at different dosages and how it changes the rheology of the mix. And of course, there's some great work done by Konstantin Sobolev on the impact of Nano Silica on high range water reducer efficiency. And if you look at our article that we published back in 2015 on colloidal silica admixture, it shows how we increased slump evolution while reducing our super P dosage by over 50%. Wow. And then air entrainment, the great thing about all nanoparticles, not just nanosilica, they do stabilize everything around it to include air as well as water for internal curing. Edgar, no problem, sir. Let me know if you have any questions. Dose number 3, stand by. There it is. Dose number 3 would be around, for CS3 is 5.46% of total cementitious, and that's dry nanosilica. Okay, Chapman and Brazier, we already got that. Squared, thank you, Josh. Please send me the name and specs of the microscopes you use for those. Yes, I think I can. I have those raw images. And you know what? Better yet, if you just go over to my blah, 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 my PhD, it goes into that in raw detail, Matt, and, into detail ad nauseum. And that is full free, sir. So please be inclined to go check it out. I'm going to see if I can find it here, which one we use. I don't want to waste too much time doing that. Whitney's going to yell at me here in a second to get back to. Yeah, I tell you, if you go check out my PhD, and again, you're not paying for it. It is for free, but it goes into everything that I did ad nauseum, and it gives you all the information to recreate it. Okay, here it is, man. Matthew, it is an FEI Nova NanoSim 630, capable of high resolution imaging on non-conductive materials. And I go through the polishing stats of ethylene glycol and ethanol and the grits that I use. But yeah, please check that out, man. Okay. Chaplin, can you talk about the optimum percent used? No, I can't, Hater, because it really depends on the objectives and the end use. Optimum use can be related to cost, and optimum use can be related to, we don't care what it costs. It just needs to be durable from now until the end of time. And then it's the cement, it's the chemistry that you add to it. So it's really hard to just focus on the best type to use. It's more what best suits you and your concrete mix design. And shoot, yes, I will try and remember to do that, sir. I'd ask Mallory and Whitney to take some notes. Hater's just asking me to send. You know what? I'll include the link to it in this. So Hater, if you just come back to this, I'll include the link in this LinkedIn Live thing. Why, thank you, Matthew. All right, let's get back to this, folks. Dun, 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 dun. Analysis and summary. So this goes back to Hader's question. Is there a perfect particle to size to use for one specific use or for all concrete mixes? And the answer is no. And that's something that separates the manufacturers, whether you're using mixed in or topically applied or injected. There are so many different types of particles, nanosilica particle uses and distributions, and we really haven't even gone outside of the ASR discussion. There's steel corrosion, there's calcium oxychloride formation. There's a lot that you would need to know for ASR. I mean, if we even narrowed it down to that, it depends. Are you using straight cement? Is it a type 1L? Is it a type 1-2? Are you combining a silica fume slag, class F fly ash, and are you using mid-ranges or normals or polycarboxylates? There's a lot of questions that we could ask before we point you. And when I say we, I'm talking about the royal term of all the manufacturers and distributors out there to help you get the right particle for the right use or the right distribution for the right use, especially when it comes to ASR. So we saw the smallest particle size was an earlier impact on the reduction of expansion, but it lacked a positive impact on expansion at later ages, and that means the growth over time. With CS2, there was little to no impact on reduction of expansion, but there was immediate expansion. But over the later ages, obviously there was more positive as we added more. And the same thing can be said for that largest particle distribution, that 45 to 47 nanometers. The bullet points and the key tickets to take away from this was the addition of nanosilica to cement, reduce the amount of calcium and increase the amount of silica. The addition of nanosilica to cement reduced the expansion due to the polymerization change, the morphology that we looked at of the ASR gel. And then the increase was found to be proportional to the percent addition and increasing the size of nanosilica. So more that you added and the larger it got, the better the resiliency to ASR gel expansion. From our micro and macro, we noticed the reduction in expansion, change in morphology, that change in chemistry, creating that environment that wasn't conducive. And then ultimately what we found later on throughout the rest of the research, when you'll get into my PhD, is we changed the phases that calcium silicate hydrate, specifically the silicone tetrahedron that are in that calcium silicate hydrate, implying that the overabundance of silica not only treated that pessimum to get past the point where the ASR wanted to thrive and survive, but we're creating a stronger matrix that'll be more resilient to that expansion when it does occur. Okay, so now what does this mean? What are our goals? We've gone over everything from talking to folks in the industry about how to use nanosilica as an admixture, using it as a topical agent. What we know is the research has been done ad nauseum. We've got a myriad, a manifold, a wide variety of ongoing ASR problems, as it turns out, Class F fly ash died years ago. It is not the same Class F fly ash that we got in the late 90s, in the early 2000s. We have a limitation on lithiums that we used to use to treat ASRs. As it turns out, there's a limitation on all the mature technologies. Even silica fumes are going to steel production and other industries. And the thing that just adds to it, the quality of our aggregate is diminishing. I don't care where you're at, whether you're in New Jersey going from river rock from the 40s and 50s to chip blue rock now, or Ohio, Colorado, we're just using more reactive aggregate that is increasing the sensitivity to this ASR gel mechanism, or the tendency. We've been using nanosilica in a colloidal suspension for decades. The commercial success has been proven through companies, through DOTs, through federal agencies all over the world. Now the idea is we've got to educate the industry. And if you're one of those naysayers, there's no way, I'd love to try and prove you wrong. Before I open up the floor for any questions, I want to show you how real and nasty this problem can get. And I think it was Hader who asked, do we have other books? The ABCs of ASR does a great job of showing you all the different things that are associated with ASR to include ultimate failure. And one of the things that I love looking at not only is the failure, but how the failure is repetitive, not only from the Isle of Man cracks, the 120 degrees that go off of each of the 3 legs, but also that gel that oozes out of the concrete when the failure ensues, not only at the beginning of the end of its life, but also at the end of its life. And this is a real structure being used on the Western US. And what you see there is not a horror movie, but ASR formation, so that the gel is being squoezed out of the concrete with iron oxide from steel corrosion and failure. Now, if you have any more questions, I am more than happy to entertain them. There's more information out there, not only on our CSCA channel or CSCA website, but also on our YouTube channels. And we're always available to answer questions. Thanks again for joining us. Don't forget to check out CSCA. And as always, we've got do we have a discount today?
Yes.
You get a discount.
CSCA 5. I thought it was 6.
CSCA 5. That is is there space between the CSCA and the 5?
Altogether for 25% off membership.
For 25% off membership. Individual membership, small business, corporate. All of them?
And,
even the student one?
Well, the student one's free.
Oh, the student one's free.
And that's through 11:59 p.m. tonight.
All right. So get that membership ordered. And yeah, let us know what questions you have. Okay, so I got one question. Oh, can you provide your contact? Heck yeah, I can provide my contact. You kidding me? Buddy, I would love to. Let me do that right now. Maybe I do that in the beginning. Oh, wait, let me. I don't. Okay, here. That's me, John at intelligent-concrete. Ooh, that's not how you spell concrete.com. That's not how you spell .com. Oh, it's limited to 50 banners. Okay, add banner. Boom. That was it? That's the only question? All right. We'll give you all a few more minutes. Let me know what other questions you have. If not, thanks for joining us, and we will get those certificates sent out. Mallory, wow, you've got your homework cut out for you with certificates. Yeah, I'm not seeing any more questions, love.
Yeah, I'm not either.
I need to get some water. All right, y'all. Well, thank you for joining us. Stay tuned for our short course number 7. Number 7. Go concrete!
Beat asphalt.